Morning, everyone. We're just waiting for a few more people to come in, and then we will start shortly.
Morning.
Morning.
Okay, Manu, do you want to take it away?
Sure, thank you.
The Strategic Innovation Fund is investing £450 million in energy network innovation, because the challenge of rapidly decarbonising our energy networks is enormous. But we can do this. With collaboration, we can make the leap. A giant leap together. We need the bravest, brightest, boldest change makers from across the world to work with Innovate UK, Ofgem and the Strategic Innovation Fund to create the energy networks of the future. The best ideas targeted at the most pressing challenges that reduce emissions and save consumers money. Join us now. Take a giant leap together with the Strategic Innovation Fund at ofgem.gov.uk. The Strategic Innovation.
Morning all. I'm just going to reshare my screen so people don't have to hear the beep every time someone joins the call. Chris, can I just check in okay from you that you can see the screen again?
Yeah, we can see that.
It's all good.
Perfect. Thank you so much. Well, good morning all. My name is Manu Ravishankar. I'm an innovation lead for the Strategic Innovation Fund at Innovate UK. So firstly, thanks to everyone for joining today morning. You're going to hear from some of the most exciting energy system innovation projects, specifically those covering the whole systems integration theme in the round one of discovery of the Strategic Innovation Fund. Can I start by thanking all the energy network partners and especially a special shout out to the respective innovation teams who we know have worked immensely hard in developing and delivering these projects we're going to hear from shortly. I would also like to thank all the third parties who've been on this incredibly hard journey with the network partners. We very much appreciate how all of you have embraced the SIF, and of course we'll continue to work with yourself and all of the key stakeholders to refine the process to achieve the best possible outcomes for the consumers and of course for the sector. So the Strategic Innovation Fund itself has two key objectives: to achieve net zero at lowest cost to customers and turn UK into the Silicon Valley of energy. As we all know, the energy sector is currently faced with significant challenges and consumers are really facing the strain. We really feel that innovation has a critical role to play in addressing these challenges and ultimately developing a clean and affordable energy system. Now, the SIF is structured around three key pillars to support this ambition: strategic alignment with funders and other sectors. The second is delivering in agile, that includes the challenge setting process, the way the projects move through discovery, alpha and beta, and of course, how the SIF team operates internally as well. And the third pillar is commercialization, where we want to ensure that the innovation that we are supporting turns into business as usual and scales up as quickly as possible. While it is the SIF's mission to develop new products and services and processes in the energy sector, help consumers and help us meet net zero, we of course cannot do this by ourselves. We have thus developed a collaboration process, Giant Leap Together, or GLT in short, that you have just seen the video about. So GLT has regulators, governments, network operators, infrastructure developers, and innovators working together on key energy system problems to help achieve these outcomes. So the GLT has 4 phases across a year. Challenge setting is the first one, where we work with the sector to develop key challenges for innovation to address. And you'd have probably seen that we've launched recently the round 2 challenges for the SIF, which I'll be talking through a little bit at the end of this session. The second phase is ideation, where we'll work with the networks and the industry to develop great ideas and connect the two stakeholders together. The third is incubation, where the networks will assemble the different skills and capabilities required in a consortia to develop and deliver these great ideas. And the last one is acceleration. Here, the challenges will officially open and proposals will be submitted, and we will work alongside the ENA, BASE, and Ofgem to run the first ever Energy Innovation Summit on the 28th and 29th of September in Glasgow this year. So hope to see a lot of you there. The round 2 discovery projects are now in acceleration in all sense of the word. The main objective of this round has been to formulate the problem clearly, pivot if we need to, and of course, fail and learn quickly. These are all really valuable learnings, including failure, which allows us to understand what doesn't work and why, and contribute to the overall institutional knowledge of the energy transition. Finally, I would like to extend my thanks to the Innovate UK team. So David Richardson and Kate Jones and the innovation team, Chris Koenig, Thomas McGoy, Tom Poole, Amy Oswin on the PMO, Paul Whittemore on the communications, and Paul Padaruth on the commercial team. And of course, to Matt Hastings, who's the SIF Challenge Director. I would also like to extend my thanks to all the monitoring officers and the expert panels. They have been critical, without whom we've not been able to achieve the round 1 of SIF. So now moving on to the challenge, I'll start to provide a very quick overview of the whole systems integration challenge. As you all know, meeting the net zero commitment is a systems transitions journey and one that needs whole systems thinking and approaches. The value of taking a whole systems approach has been estimated by several people, and I'm not going to repeat the message. But the key common finding is that the value is significant, and it is certainly worth pursuing. So the aims that we set out in the challenge last year are to improve coordination between networks and other system participants, to reduce duplication and excessive variation of products, processes, and services, to reduce complexity, bureaucracy, and barriers to entry, improve coordination of emerging innovations across networks, generators, market participants, investors, local and national policymakers, consumers, and other key stakeholders, and finally, to understand consumers' preferences to inform future market designs, which will help to optimize across networks and infrastructures. Some of the specific areas of scope we asked the projects to consider were coordinating across energy transmission, distribution, and system operation across vectors, so gas and electricity, coordinating approaches to siting assets to deliver more efficient capital investments on the system, evaluating the costs and opportunities of repurposing or decommissioning existing infrastructure or assets, and thinking about how to maximize efficiency in large-scale energy networks and system investments by taking a systems view across generation and demand side linked to decarbonisation. So we have grouped the projects into 4 themes, as you can see on this slide. So these 4 are clockwise: increasing flexibility sources in the energy system, hydrogen deployment and integration, circular economy for resource efficiency, and new technology development for renewable energy integration. So in the first session, we will be covering new technology development for renewable energy integration. Here we'll have 3 project presentations, and then we'll be going into the circular economy for resource efficiency theme, where we'll be hearing from 2 projects. So very quickly, in terms of the structure, so as you can see at the end of the 3 presentations, we would have about a 10-minute, 5 to 10 minute, sorry, a 10 to 15 minute Q&A session, where I will take the questions that you put during the presentation, and then I'll ask the presenters to come on video to kind of answer these questions. So if we could ask you, as these projects are being presented, as you think of questions, please put them into the Q&A chat so that I can pick them up and then put it to the presenters at the end of this. And then we'd have a 10-minute break between the 2 teams. And of course, at the end of the session, I'll talk a little bit more about the future challenges and also the Energy Innovation Summit. So without further ado, can I now hand over to Alexander Yanushkevich from National Grid, please, to take us through the Skedon project. Alex, are you there?
I can see Alexander actually on the list of attendees. So perhaps if we skip to the next presentation, and I'll try and get hold of him.
But the next one is Alex as well, so I might skip to the third one. So Simon and Ben on the call. Oh, Martin is here.
Yeah.
Oh,
Hi.
yeah.
Okay.
Sorry to jump
if
to you
we
guys
move to
straight away.
That's okay. If we take it away then, so if we move to the next slide. And the next one. So welcome to the Network DC Show and Tell. So I guess when we last talked, we talked about the benefits that we saw potentially from multi-purpose interconnection and the DC networks in the context of providing greater capability. This comes from also a more rationalized construction of the offshore network. So as you can see in the diagram on the right, the squares indicate HVDC elements, the circles indicate AC elements from the phase 1 coordinated offshore work, which the ESO and others conducted as part of the OTNR exercise. Where you see squares and lightning bolts within them, these were DC hubs. You can also see in red on the south coast, there's a number of HVDC interconnectors which have intermediate offshore points, which would be multi-purpose interconnectors, which as they scale, again, could consider using DC hubs. So essentially what DC hubs allow for is, much as the AC system, a rationalization of assets, so that each supply of generation to point demand doesn't require discrete circuits of its own, but can be pulled together in a network that then can maximize capability and minimize infrastructure. So if we move to the next slide. So this really describes the counterfactual, which is on the left. So you can see the sort of crazy paving of point-to-point connections that you can get across, in particular the east side of GB, in a world where you do essentially point-to-point connections. Now, in the world of network DC, you have the ability to build these consolidated hubs of transmission capability, whether they are related to interconnectors and the assets being maximized in purpose to connect wind farms, or if these are arrangements which allow high levels of transmission in parallel across the network, as you can see the hubs in the northeast doing. So fundamentally, the challenge surrounds the technology of the DC circuit breaker within an AC substation. We have a well-developed infrastructure of AC circuit breakers, which are designed to interrupt faults. For DC, that infrastructure has only been developed within China. The operation of those DC circuit breakers and their technology is a good deal more complex than an AC circuit breaker. And so there are the twin challenges of identifying the requirements for a DC circuit breaker, and that's in terms of the use cases where DC circuit breakers are required, but also in terms of what specifically you're asking them to do within those use cases. And there's also that challenge surrounding understanding the delivery of that, how you achieve it. Right, if we move to the next slide. So essentially, what are we trying to achieve in Network DC? What have we been doing over the last 2 months? Well, what we're trying to achieve is a streamlined HVDC network where DC circuit breakers become these new hubs of capability. The principal benefit that we found for the use of DC hub technology, unlike the Chinese case where it's been a maximization of reliability primarily that's driven DC circuit breakers. They're used predominantly on DC overhead lines in China, which are of course susceptible to lightning strikes. Within the GB system, with our system having a limited scale, being an island network, it has particular vulnerabilities to maximum loss of power, and it's really in limiting those maximum losses of power that the DC circuit breaker has its true value. So as you scale the concentrations of offshore wind within those, or indeed in the future, if there was a large scale of hydrogen, the ability to use DC circuit breakers to limit the scale of the loss is critical. And now we mentioned the uncertainty. The key uncertainty, I guess, is the difference between China, where live testing is very much a part of the verification of circuit breakers. So actual faults, AC and DC, will be applied to these networks to verify the simulation analysis and to hone the specification of those DC circuit breakers. And there's been an evolution in specification in China based on their deployment of their projects over subsequent developments of technology. So they've modified the overloads, they've modified the durations that DC circuit breakers are expected to operate over. There's a question around how exactly you integrate these into the DC system. So what are those use cases? As I say, ours would be more around submarine cable application. There's the questions around dimensioning those solutions. There's a question around defining the requirements in terms of the frequency response limiting requirement. So how quickly can you restore your network from a DC circuit fault, and also the operability considerations. How do you manage outages, depletions, limitations in circuit breakers capability over their operation? The benefits had yet to be costed. We've now done an initial costing, and equally there's no defined process for how you would implement in a GB context where we don't have live testing on the mature system as a rule, and so we would look as a default for demonstration to be enabled by specific simulation and definite design process and testing. So that's what we're trying to achieve through Network DC. And I'll now hand you over to Martin, who will take you through the initial retrospective work over the last 2 months. Martin.
Thanks, Ben. Yeah, so my name's Martin Wilcox from Mott MacDonald, and I led the contributions from Mott MacDonald to the discovery phase. So if we can just move forward probably to the next, let's move through this slide into the next one. Thank you. So we had two purposes in the discovery phase. So the first purpose was to try and quantify, or to begin to put down on paper, what are the benefits of DC circuit breakers to the GB system, and how significant are those benefits? And secondly, we wanted to identify, so what kind of confidence building measure or market intervention is required to encourage adoption of HVDC circuit breakers and break that chicken and egg situation and get the first DC circuit breaker scheme underway in the UK. So what we've done under that second piece of work is we've sketched out a route map through alpha, through beta, and critically what you could find in our report is a table at the end that says, well, what remains after beta, between beta finishing and what's left for the industry to do to get that first DC circuit breaker scheme underway. To put that in more kind of formal procurement language or engineering language, we've provided a route map towards the necessary front-end engineering design or feed that is always essential in a project like this in order to have enough technical information to write a tender and to go out to tender to manufacturers to provide and design and deliver the first DC circuit breaker in the UK. So if we move to the next slide. So within the project over discovery phase, we looked at and considered 4 potential different ways that you could try and remove first mover hesitancy or concern around DC circuit breakers at the moment. And we deliberately kind of painted or put a number of options on the table, including the extreme options. So what I mean by that is that we considered option A here, which would be a kind of a light touch approach. In essence, doing more work, looking at the academic literature, trying to have more one-to-one engagement with the projects, the manufacturers and the real schemes that have been developed and commissioned, try and learn operational experience from them. And as Ben's already indicated, a lot of that operational experience is in practice in China currently today. We also looked at the other extreme. So the other extreme is represented by option C here on the slide, which would look like a significant kind of government support through Ofgem, through SIF, of capital investment into the first DC circuit breaker scheme. So that would significantly reduce commercial risk associated with that first DC circuit breaker design. Now, in all of this, customers are really vital. So a contribution through the Strategic Innovation Fund is essentially a contribution from yours and my energy bill. So it's really important to decide and to determine what we think is a proportionate and kind of necessary and sufficient support to DC circuit breaker adoption in the UK. So if we move to the next slide. So how do we go about deciding what is appropriate? So what we did was we tested this against the needs of the stakeholders, and the consortium that SSE had brought together was a very convincing consortium that essentially represented many of the stakeholders in this discussion in the industry. And we then added to that with a questionnaire which went out to manufacturers from Ben via the National HVDC Centre. So within the consortium, we had the stakeholder representation from the system operator, National Grid ESO. We had representation from transmission asset owners, developers and planners in the form of SSE themselves. We had representation of companies operating interconnectors, operating offshore transmission assets, and we had representation from the renewables industry, both through the Trade Association and also through the Carbon Trust, who run one of the important collaboration vehicles through which offshore wind developers collaborate on research and development. And through that process, having kind of put down and documented the stakeholder concerns, we think we were able to identify, and we have identified and put forward what we feel is a middle ground, which balances cost to the Strategic Innovation Fund. Therefore, it balances cost to consumers. It doesn't take away all 100% of the risk from commercial developers. But really importantly, it does bring forward a convincing demonstration that, as Ben alluded to, is relevant to the GB. It recognises the physical geography of the GB, which therefore leads to cable lengths and offshore lengths and so on. And it also, you know, for want of a better word, recognises the electrical geography of the GB, which again is different to situations that have currently been installed in. So what this middle path looks like is encouraging HVDC manufacturers who've been involved in DC circuit breaker design to date to tailor their designs or to modify their designs with specific case studies and specific network design information provided to them about the GB context, which would have been agreed with the stakeholders. They then go that next step in turning those new or tailored designs, hard coding that into the protection and control systems of their HVDC circuit breakers. They then bring those to the National HVDC Centre in Cumbernauld near Glasgow. At this point, these are essentially looking very much like your average IT server rack. So we're not talking about massive pieces of equipment or significant capital investment. This is mainly talking about design and development time. But by bringing those racks to the National HVDC Centre, you're then able to do a really convincing demonstration of what this would really look like in practice operating in the GB network. So if we move to the next slide. So what I've got on the chart here is our overall kind of flow chart of activities that we carried out in the discovery phase. And I've talked about the majority of the bottom half here, number 2, how we accelerate adoption. And as you'd imagine, once we develop that preferred option or that middle ground, we close that out by identifying roles and responsibilities, ensuring we had the right members of the consortium, and putting costs and timeline against the activities in alpha with a look ahead to beta. The other half that I talked about was quantifying the benefits or phrasing the benefits of DC circuit breakers. And that's shown here on the top flow chart. So what we did there was that we developed case studies which have got really strong strong stakeholder support behind them. And in fact, you know, we continue to see more stakeholder support for those case studies that we've developed. We kind of went through a process of testing ourselves and ensuring that we could say in words what the benefit was. And then we did go through a process of then beginning to put numbers against both the costs and the benefits. It is still at a discovery stage of maturity of cost and benefit. So we have more work planned in Alpha, but I will at this point hand over to Aurelia, who can tell you a little bit more detail about that work that we've done in discovery.
Thanks, Martin. So we've been working a little bit on the cost benefit analysis with the information that we've been able to get hold of at this stage. There's certainly quite a lot of work to be done to refine the case going forwards. If we could just pop to the next slide, that'd be great, thank you. So as an enabling technology for an HVDC offshore system, the DC circuit breakers present a number of benefits, and we've been able to quantify quite a few of these. Most importantly, the response time to a fault, which results in reduced ancillary services expenditure. But over the lifetime of the assets that we've been looking at in the use cases that we've studied, we've been able to show that essentially over the lifetime of the assets, the benefits that we can currently say will be monetized vastly outweigh the costs associated with implementing the system. And this is based on a number of things, but largely on the reduced ancillary services expenditure. And I will pass over to Ben to talk us through how we've arrived at that conclusion.
Hi everyone, back again. So if we move to the next slide, I've got some wibbly wobbly lines. So those of you familiar with system frequency, it's essentially the balance between the generated power and the demand on the network. Now that system has an inertia which resists the change in frequency, so it doesn't instantaneously move to a new level. So the long and short of it is, if you lose generation, the frequency drops. There's an imbalance between the generated power and the demand. That means that the system begins to slow down, and if you lose demand, the frequency rises. So in the context of a generation loss, the frequency dips, as is shown on this figure. The normal dip would be in green, so it drops towards an excursion limit on the system, and then it's recovered within limits of normal operation, and it will wobble around a bit as generators recover and their power normalizes following the event, and additional secondary response and reserve is provided to the system to both recover and manage the enduring deficit on the system. So essentially, what you've got on green is what happens in a world of today, and it's the capability that you can achieve via network DC. If you take an example of, let's say, turning in one of these MPIs into a 4-switch ring with about 4 gigawatts of connection to each of the corners of that arrangement, then if you were to compare that against the counterfactual of not doing that, but putting all 4 gigawatts on the DC circuit, then within half the speed of light, the voltage would collapse and all that power would be lost. And then within a couple of seconds, you would, if you'd installed high-speed switches within the arrangement, and in particular, if you looked at a full bridge arrangement, you would be able to bring back the power. But a couple of seconds in eternity in frequency response. Frequency response is delivered from about 1 second onwards, the fastest of the frequency response available. But we also have this thing called rock-off that you can see on the slide, which is the gradient of the frequency for the rate of change of frequency. So if that exceeds certain limits, then again, we start cascade tripping generation. So when we're talking about 4 gigawatts, that's roughly, just over twice the capability of the system today, with a maximum in-feed loss risk of 1800. And in practice, that would vary across the year. In order to achieve a rock-off that's respected, then what we need to do is to add more inertia to the network and more response to the network to both buy time for that frequency fall to be managed, and also to then recover the frequency from that overall deficit, which is now larger. And that's what you're seeing in the orange. Now, the point of that intervention is that when you cost that up, the single intervention for a single hub is already into the several billions of pounds. In fact, it could easily get into the 10 billions of pounds, because the level of inertia intervention is more than the minimum inertia limit that the network is currently held to. So that's either via annual contracting or a market mechanism, a significant intervention into the system. The counterfactual of infrastructure that would avoid that risk by building point-to-point links involves several additional pole converters for each of those gigawatts exceeding 1800 megawatts. So again, you're into billions of pounds of cost. So however you look at it, even if you accept that you'd be able to take up that environmental hit, there's still an impacting cost of several billions of pounds, and that's alleviated by DC circuit breakers, and that's a scalable solution. So it's not just for that first scale of hub. As the hub scale increases, just like on an AC substation, you don't have to build a second substation, you just extend the existing one. So it has a sustained benefit over the life of the projects which are growing onto that network. It's the same analogy as the AC system. The costs are different, but in principle the benefit is significant. Okay, I'll pass it on to the next slide, and hopefully Simon's joining us for that one.
I think is Simon here, or I think he'd got a clash with another presentation.
Yeah.
Well done, good.
Yeah, sorry,
That's great.
the presentation was delayed and this was brought forward, so we're now running
You've
together.
caught up, Simon. Great. I'll pass over to you. Cheers.
Okay, so I'll just go through the look ahead of what we're going to be doing in the next phase. So next slide, please. So in the alpha phase, the alpha and beta phase, just for clarity, so where we're trying to get to. So by the end of beta phase, we're really trying to get to the point where we've de-risked circuit breakers to the point where they become a viable option for installation in the future network design. What we can't commit to here is the actual installation of the first circuit breaker, because that depends on a number of things that are outside of this project, namely what the future network design will be and when those DC networks will happen. So that's where we're trying to get to at the end of beta phase. And at the end of beta phase, we want to have a supply chain with multiple vendors that are able to supply those circuit breakers that meet specifications for GB network conditions, and there are codes in place that allow those breakers to be installed. What we're actually doing in alpha phase is really we're doing 5 things. So we'll be providing greater definition of the use case. We can't say too much about that now, but that use case will be a site that is likely to be one of the first places that a circuit breaker will be installed, based on what we know about what is happening with DC links in the UK. We will be engaging with the suppliers of equipment. So at the moment, we're putting non-disclosure agreements in place with the OEMs, the original equipment manufacturers. That wasn't done in discovery because there just wasn't enough time. Anybody who's worked on non-disclosure agreements with equipment manufacturers will realise that takes time to do. We'll also be starting the process of the detailed simulation of the performance of those DC circuit breakers, which has already been talked about at the HVDC Centre, using both the manufacturer supplied models, but also open source models, which Edinburgh University will be working on and sourcing for us. We'll also be looking at the commercial arrangements for how those circuit breakers might be installed and managed within the network, both commercially and also from a regulations and a standards point of view. And in line with guidance that we received on cost benefit analysis, we'll be continually revising the cost benefit analysis. Discovery phase was if you like, a high level cost benefit analysis, but we'll be refining that and adding more detail to the cost benefit analysis in alpha phase, and then again in beta phase. So we're hoping that we can get to the point where we'll have no significant technical, regulatory or commercial barriers to the development of onshore HVDC hubs, but whether or not they get developed entirely depends on the trajectory that we take within the UK network, and that depends on a whole range of stakeholders, which are really beyond the scope of this project. Okay, that's the forward work plan. Next slide, please. So I think that concludes our presentation. If you'd like any more information on the project, then you can contact me. I'm the project manager. I'm simon.stromberg@sse.com. If you're interested, we're always interested in people who want to get involved, who are stakeholders, who have an interest in the project. We're always happy to receive information, thoughts and ideas as the project continues. Okay, that's the end of the presentation, and we're open to questions.
Thank you, Simon. So I think the way we've done it is, as you said, we brought your presentation forward. So we're going to go back to Alex to finish the other two National Grid presentations, and then pause in about 25 minutes or so for questions. So yeah, thanks, Simon. Thanks, Martin. Thanks, Ben, for your presentation. We will come back to you in a bit. I'm going to move back to Alex. Can I check that you're online now?
Hello, hello.
Hello, how are you?
Apologies, there is another data individualization call. I'm also presenting. Hope SSE didn't mind to go ahead.
I think we managed to make it work. So yeah, thanks everyone for their flexibility.
That's fine.
Alex, over to you.
Okay, thank you, Mano. Okay, Scadent, our project that was focused on developing or investigation how we can use superconducting cable applications in urban environment. Please go ahead to the next slide. So that's where we started basically last year, summarizing what could we do to investigate how it can be done, and address the main challenge which we see in urban environment, how we're going to power all electrical vehicles, increasing heat demand with heat pumps, as well as normally growing demand for electricity in urban environment from the industry, as well as upcoming data applications. And here we're meeting the challenge of aging infrastructure, slow consent and construction times, and community disruption if we need to replace cables in urban environment. One of the solutions that's been around for a couple of decades is HTS technologies, high temperature superconducting cables, and that demonstrated benefits for medium voltage networks. There is one system running in Germany at 11 kV that replaced one 10 kV system. And here we wanted to have a look, can we use 132 cable systems to either replace 132 conventional cables to increase capacity by 3 to 5 times, or we use 132 kV technology replacing 400 kV, meaning that the substation can be smaller. We don't need to use SF6 technology. We can go with different insulation media and probably give us more flexibility as well as cost saving on the infrastructure. Okay, next slide. So to achieve that, we got quite a big consortium. If you click next, does it? Yeah, get all these slides, yeah, things together, it would be easy. Get a big consortium of partners. It was us, National Grid Electricity Transmission, SP Network, UKPN and WPD, representing the networks. As 132 is between transmission and distribution, I think it can have a big applications on the both sides of the transmission distribution network sides. We worked with the Strathclyde University and Manchester University that look into literature review and what the requirements are there from testing of this technology. And we worked with Nexans and American superconducting companies that work together to develop and build those HTS systems. They recently finished one project in Chicago, and Ørsted represents a generation stakeholder, and Fraser-Nash was helping us with technical economic assessment and innovation project management in the project. Next slide, please. So first of all, is technology there? So we look through the existing technologies from Nexans as the main partner in the project as well. We should look to alternative supply chain providers of HTS technology in Asia, for example, in China, Korea, and Japan. So what we found out, there is no significant challenge to design and produce 132 kV cables at 4,000 amps, which represents almost 1 gigawatt of power delivered. That cooling systems that need to be used to cool nitrogen can leverage from a growing market for liquefied natural gas cooling systems, that we can achieve huge savings to use basically business as usual technologies. Installation of a cable itself is quite similar to conventional cable. It has very similar dimensions as 132 kV cable. It's a bit more challenging to install the joints, but they run in 500 meters sections. So for 5 to 10 kilometer systems that normally used in distribution networks, we don't need as many joints, and obviously the termination look a bit different, as well as we need the cooling system. There is a standard, IEC standard, developed recently in 2019 that covers HTS cables for high voltage applications, and that it's been developed recently and not widely adopted. So we reviewed, and it covers most of the applications we could consider. And what we identified, these cables have quite low failure rate, mainly due to external damage. For example, learned from the system that I said has been running in Germany for several years. So how HTS cable looks like, you can see in this picture, is basically the cooling medium running in the middle, and there is a layers of superconducting cable, which surrounded by insulation media and outer cooling system that covered in the basically rubber or plastic as a conventional cables. Next slide, please. So if technology saying it's can be done, on the other side, technical economic assessment was always a challenge because it's obviously HTS cable is more expensive. However, in this case of replacing 400 kV conventional cables with 132 kV cables for generic 5 kilometer cable system, we identified as the NPV of these both applications are very similar, as you can see on the graph. Where HTS is very sensitive to infrastructure requirements, and especially the beneficial where we can avoid building a tunnel and rather, just go directly buried cables, for example, for smaller, more compact installations. What we need to understand, we didn't have much time to identify which exact locations it can be used, and how economy of scale can affect the future cost-benefit analysis. Because up till now, all HTS systems were bespoke made for particular applications, particular networks, certain counter requirements, and so on. What we'd like to achieve in this project to make a more standard design of a cable that can benefit from an economy of scale, as it can be used globally, and it will drive manufacturers to invest more in manufacturing capabilities, and thus driving the cost down. Next slide. So what we see the next phases for this project is design, test, trial 150 kilovolt, 2000 amps and 4000 amp system, which covers most of the applications around the globe, in the UK, in Europe, in the US, and in Asia, and thus creating the market where more HTS systems can be used at a certain power ratings, similar as we use for transformers. There is a certain typical ratings or circuit breakers. That's what we'd like to achieve. There is a certain standard design for a certain standard rating, and networks from around the globe can use the technology. That's why driving the bigger demand for these technologies, as well as they don't need to made bespoke, not retested, and so on and so on. Understand lifetime performance for maintenance or repair requirements, especially for us as networks in the UK, as we never experienced working with them, and we don't have a good experience with using oil filled cables. That's why it's quite a resistance from many stakeholders how we can achieve lifetime performance of this equipment and minimize maintenance requirements, repair requirements as well. What we like to investigate, how we can improve resilience to external damage risks, and how to fast repair these damages if something happens, as well as assess effects on the electric network from fault levels and power flows, because obviously if HTS is the lowest resistance in the network or impedance of the network, it means that there is it affects the power flows, as well as it strongly affects the fault levels. So when we investigate where it could be applied, we also understand which fault levels and power flow effects these HTS systems could have in urban environment. And last but not least, which often was neglected, is what do we do with this such amount of power at 132 kV inside a city? Because normally at 132 kV it's about 250 MVA substations. So meaning that we need to rethink how we design the substation to adopt this amount of power and distribute it around the network. So working as a hub that all this power delivered from the outside substations and then distributed in the city. That's all from me. This project.
Thank you, Alex. Zemi, are we staying with you for the Segel presentation as well?
Sure.
Okay, over to you.
So go next. So if in SES Cadent project we look into how we can deliver power in urban environment, in Segel projects we're looking into how can we deliver power to the cities from the offshore wind or from different parts of the country the most cost-effective way. So there are quite a challenging task we have ahead, how we can deliver power of 40, 50, 60 gigawatt of wind on the East Coast to big demand centers like London, Birmingham, Manchester, and so on. And there is a big opposition to construction of overhead lines. And if you look on the transmission network, the East Coast is very underdeveloped regarding the transmission. Please click next. Yeah, open them all, please. Okay, good. Yeah, so what we propose to use gas insulated lines that can compete against the cable system and the higher capacities, and can deliver high amount of power of 3, 4, up to 6 gigawatt of energy from offshore to onshore, underground, with underground transmission. Okay, next one. So what is GIL? GIL basically is a pipeline with the conductor in the middle and surrounded by the insulation gas. And when compared with the conventional cables, it has a much higher capacity, especially if you consider longer distance. As I said, it can deliver with the 3 pipelines, one per each phase. It can deliver 3, 4, up to 6 gigawatt of power at the high voltages. It has a lower capacitance against the cable, so there is a less problem with the grid stability and reactive power compensation. It has low electromagnetic field because it's shielded by the pipeline, and especially could have a longer lifetime due to lower electrical and thermal cycling, meaning that it can run for decades, similar as we have gas transmission infrastructure. Next one. So why it's not used today for long distance transmission? First of all, it's a lack of experience, because today where we use gas insulated lines that build inside control environment, inside substation or industrial estate, where there is 24 hours access to it. It's basically designed specifically for this operation to deliver it over a short distance where we have constraint of space, deliver big amount of power. And the other problem, which might be even bigger, that the current generation of GIL are filled with SF6, either pure SF6 or a mixture of SF6 with other gases. That's obviously is not accepted anymore to introduce more SF6 into the system. And that's why in our project, on one side, we're trying to design GIL for longer distance transmission, optimize it for a bigger, longer transmission, as well as optimize for lower maintenance. On the other side, we're looking how we can replace SF6 in these pipelines. Next. Next, yeah. So what we discovered during discovery phase, first of all, on technology and costs, there are several big manufacturers around the globe that can build and deliver GIL systems. So there is significant supply chain for GIL technology, conventional one. One of the biggest costs is the material cost. The pipeline is made of aluminum, so it's quite a significant price in the total project. And also cost depends on the route. So depending on the geography, how many river crossings, how many road crossings, how challenging it is to get across the estates, or what is good GIL for. It can easily make 90 degrees turns. However, like it has a limit how big is the turn or inclination over the distance. Second one, SF6 alternatives. Again, we found SF6 alternatives, and there are 4 of out of 7 companies offer SF6 alternatives. This includes Nova Gases, which is a brand name for one of type of the gas developed by 3M. There is proposed air, the proposed nitrogen and CO2 in various mixtures. However, the problem with air, nitrogen and CO2, because they have lower electrical strength than SF6, meaning that the pipeline should be bigger to create enough clearance distance, meaning that the pipe gets bigger, more material, more costs. See point in the previous column. So the most promising one could be Novec, that is made by 3M company. However, it's still in the smaller proportions, and there is not a dedicated production to equal to the scale of SF6. Although if we see benefit of SEGIL and demonstrate it can be applied on the network, obviously it will require a big amount of this gas, meaning that it will drive the costs down. And Norway gases have very similar dielectric properties to SF6, which has already been demonstrated in the shorter GIL sections in the substations. So supply chain and installation, GIL sections made of complete modules. Today there are like several meters. What we would like to go for is up to 100-meter sections. So to make it easier to install and more cost effective. They can be joints either bolted together, bolted flanges, or welded. So that's what we would like to investigate in that next phase, which is more effective and maintenance free. And installation itself is very similar to gas transmission pipelines, and we can leverage benefits of gas transmission here, experience in construction and operation. Although gas transmission is running at much higher pressures, 100 bars, where normal GIL or GIB systems run at about 7 bars. So it's a bit different, but from the construction point of view, it's very similar in this sense. Okay, next slide. From cost-benefit analysis, we try to identify where the biggest drivers for the cost. First one, as I said, it's 40% is aluminum, is the biggest material cost. So reducing the size of thickness of the pipe will have a large cost impact. It will be part of future design works to understand how it can be optimized. Pipe manufacture is not fully utilized. As I said, it's basically designed and built for different applications, smaller sections, smaller projects, up to several hundred meters. If we talk about multi-kilometer, 10, 20-kilometer pipelines, then we can clearly see benefits there from the cost point of view. Civil in the installation, as I said, the route is it's a big question, so it will depend the cost from project on project, although it's not much different from cable systems, where it also route dependent, how many river crossing and road crossing and what is the turns it has to do on the way. And if we go for longer GIL section, we can reduce cost to install them and join pipes together. And yeah, type of the ground has a large influence on civil costs. And about 20% identified is planning, design and permits and other benefits. So GIL have lower power losses in operation than cable systems because there is a less capacitance, so there is a less reactive current required, and potentially have a smaller footprint than cables, especially if we talk about high capacity lines where there should be 3, 4 or 6 cable circuits installed next to each other. Okay, next slide. So looking ahead to alpha phase, what we'd like to do is investigate how we can reduce the costs and get more parity against the cable systems. Optimize the gas mix, which gas we can use to replace SF6, and pipe size, and basically the one section design. Deliver a FEED study for a selected route to investigate what are the challenges of manufacturing and installation and operation of the GIL. Here we would like to take one of the National Grid visual impact projects recently built to investigate how it, if we use GIL, what could be the challenges. Refine the benefits case to clearly understand what the benefits and how much competitive it's against the cables, and where is the break even at what power rating, and basically design a system for a certain power ratings that we see in the future. Here we work with National Grid ESO that looking on the onshore coordination network understanding how much infrastructure has to be built to connect all the offshore wind in the next 10, 15, 20 years. Would like to understand also the full life cycle costs and understand how we can maintain and repair if something happens to the pipelines. Obviously, it's a pipeline, it's more robust against the external damage than conventional cables. And then a beta phase, if all goes well, we're planning to build a demonstrator to test it in the real environment and run through the type testing, certification testing to adopt this technology for future use. That's all from me.
Thank you, Alex.
Thank you all.
So I think now we'll move on to the Q&A session. So if I can ask the presenters to come on video and off mute, please. Thank you. So a few slides to skip through. Perfect. So yeah, we've had a few questions come through, and appreciate that, Ben, you've been answering some of these in the chat. But I think for the sake of recording, I'm going to put the questions back to you, and I'd appreciate if you're okay to kind of answer them. So I'll start off with the network DC project. Perhaps have you considered the TRL of DC circuit breakers and the readiness of the supply chain?
Yes, so promotion sort of puts the TRL in Western Europe at about 6-7, but in China it's 8-9. They're actually deployed and in service. There's about 20 of them running, but they've kind of done a bit of a transition. They started with mechanical DC circuit breakers, which were kind of blunt force objects to interrupt current, and they've progressively gone into more elaborate hybrid devices over time. They've refined their specifications. They're now standardizing, hence why it's not really 9 just yet. Whereas in Europe, the promotion work is kind of where it was left, and that showed conceptually DC circuit breakers should work in these submarine cabled environments that Martin mentioned, but it hasn't focused in on the specifics of how you do that. So we're particularly interested in not just about the interruption of overhead lines, but cables, and we want to understand how we limit loss and how we manage the capability of those networks over time. So when there's an outage, when there's a redundancy or a limitation to the DC circuit breakers, how do you handle those? How do you test it? So there's a whole bunch of stuff that we have to add. That's all right. Cheers, Tiblin. Take care. But long and short of it is the technology is available in concept. It's available in practice. Vendors have the devices. We need to demonstrate how we want to use them, and we need to specify accordingly. And I think that's where we're at now, that we can see clearly what those use cases would be, what the practical example would be in the alpha phase, then to take forward and get vendors to comment on something that could potentially be a real use case.
Thank you, Ben. I'll do one more question to you, and then I might speak to Alex, and then we'll come back to you if that's okay. Does your CBA consider a scenario on circuit breakers versus DC switching station for, I'm assuming it's multi-point interconnector integration?
Yeah, so this is it. So the approach of turning the whole DC network arrangement off and then switching it back on again is an option, and you do that via these high-speed switches, which identify from where the faults are, how to isolate the network quickly. But to do that, you need communications. To do that, you need to deal with the mechanical timeframes of these selectors, and that all takes time. So it's taking seconds, and the problem with a frequency event is you don't have seconds. So unlike perhaps the sort of Chinese examples where an overhead line fault, it's a network in parallel with their own, as long as they could deal with the temporary time frame of seconds for stability, thermal and voltage, that would be fine. In GB, we're taking off a lot of generation in that time frame, so we can't really afford to do it. So switching stations are helpful. You have selectors on the AC system, which allows you to have operational control of taking outages and allows expansion. And it's really in that context that selectors would be involved in a DC network, but you'd still need the DC circuit breakers if you wanted to have a large capacity network, as we've been investigating.
Thank you, Ben. I've come to Alex, if that's okay for a couple of questions, and then I'll kind of swing back to you.
Okay.
On this Skaden project, Alex, what was the cost benefit evaluation done on a cable versus cable or a capacity versus capacity?
So what we took like capacity and how it can be delivered by HTS cable and conventional cable. So that was the biggest, the cost benefit analysis. Obviously for conventional cables, we had to use more circuits. I think there were like 3 or 4 of them to deliver the same capacity. And basically that's where the benefit comes into the motorization, because HTS needs less area, so shorter or smaller footprint than conventional cables, and less installation cost because we don't need to install 12 cables, but we can go with 3 cables at the same power rating.
Got it. Thanks, Alex. And a couple of questions, I guess, from me as well. For the HTS cables, I guess, where do you see the main avenues for cost reduction? Is it going to be in the core technology? Is it going to be the installation cost, or just economies of scale and kind of learning how to integrate new tech? Where do you see the big cost savings coming from?
Yeah, so the main cost saving is where we can avoid building a tunnel, but rather go with just directly buried cable, because the tunnels are very expensive and takes a long time. So this is quite obvious: when cable, no tunnel, HTS can deliver huge value there. On the other side, as I said, up till now, every HTS was bespoke made. So what we're pushing the approach, let's make a standard design for a certain ratings that networks can work with, like 500,000 MVA. It's quite an obvious thing, and then it can be used across the world, driving the cost down, because now the kind of the manufacturing scale of HTS is very, very tiny when compared to conventional cables.
Got it. Thanks, Alex. I think we just got a new question coming from Malcolm. Have you done analysis of copper cooled at 77K? The losses are equivalent for 50 Hertz.
So meaning that not using HTS, but kind of cool the copper cable?
Yes, that's my understanding. Yeah, copper cooled rather than HTS.
No, but
yes, Malcolm is saying yes. Yeah, that's
no. We compared HTS against conventional cables, 132 kV conventional copper cables.
Got it. Maybe yeah, Malcolm can put you in touch with Alex if there's some interesting conversation to be had there for Alpha potentially. Yeah, so given the current cost estimates, I think you've mentioned this, but just a summary of what are the most effective use cases in the current cost estimates for the HTS, Alex. Where do you see that?
Yeah, as I said, avoiding tunnels, and where we need to deliver, let's say, 1000 MVA, where we today use 400 kilovolt systems. Then we basically go down to 132 kV. So then we need another 132 kV substation and so on. So what we can do, deliver it in the city into a hub, and basically use it as a middle of a spider web to distribute around the city, and then they have a smaller 132 kind of substations that deliver power directly to local heat networks or EV charging and so on.
Got it. So follow-on question from that, in terms of the timescales that we have, like the policy commitments for meeting electrified transport or heat in urban centers, like your rollout of technology, how does it positively or negatively impact some of those timescales of connecting heat and transport solutions? Is it a quicker approach?
So as we did not, at least that's what Nexans and AMSC claimed, there is not a big challenge to design and build a cable for this application. So we don't see challenge there, and main challenge is integration on the network that we see, where we don't expect big technical challenging, rather thinking about the philosophy and reliability and resilience. So if all going well, I think in 3-4 years we can have a fully developed solution to deliver 1000 MVA into the middle of the city at the the cost competitive to conventional way.
Right. One specific question for Segil, and then I think there's one kind of cross-cutting question that to you and Ben as well. In terms of, I guess, are there any supply chain vulnerabilities introduced with these new cable technologies? Given it's kind of, it looks like there's a lot of dependency that's at least more than what you have in the current cable systems. Like, do you also look at supply chain vulnerability when you're looking at this?
Okay, from Skaden point of view, we identified that there are at least 4 HTS cable manufacturers around the globe. Nexans in Europe, there's Sumitomo in Japan, there is LS Cable in Korea, and there is a company in China as well, or maybe there are a couple of them, but it's difficult always to get information about them. So it's quite diverse. And American Superconductor owns the IP for the superconducting foil, but there are different designs, different materials, and so on. So from this point of view, we don't see much supply chain challenge. From Segil point of view, we need a lot of copper and aluminum, so this could be a challenge in the future where we can get so much material to build those systems. But again, it's what we would need to investigate at the next stage in more details.
And then one specifically for Segil, then are there any, or has it kind of passed any material safety considerations? So fire, fumes, when you're using these new gases, is there any health?
Yeah, that's what we investigate in other projects, which we do through different innovation mechanisms. What we identified, those novel gases have acceptable level of risks and have much lower global how's called basically carbon footprint.
Global warming potential.
Yeah.
Got it. Okay, so the one cross-cutting question maybe, and then there's some more specific questions I'll come back to you. Just these new cables and new technology, of course, they don't operate in a silo. They will have whole system impacts. So how do you plan to test kind of these whole power system impacts of these new technology with slightly different kind of electrical properties, whether it's gas insulated lines or DC networks or superconducting cables? I don't know, Ben, do you want to start first and then I'll bring back to
Yeah, so just to let people know what we've got at the centre. So we've got the highest real-time computing capability within Europe for analysis of models and indeed real control and protection hardware. So what we can do is we can use realistic models of the onshore AC GB system, and we can construct realistic cases of DC networks that we're connecting to. So that includes real equipment specifications of cables, converters. We can use realistic components like the control and protection of the actual DC circuit breakers. So it's getting as close to reality as we can, and we can do that in quite flexible ways and then throw scenarios and throw faults at it that allow us to contemplate how the overall network's going to respond. So it's not just about making sure the DC network is resilient, it's understanding what that means for the AC system when it sees an interruption on the DC side and vice versa. So there's quite a lot that needs to be looked at, but building that simulation environment is something we're all across and we can see how to do.
Alex, do you have any comments from Skaden or Segil point of view?
Not really.
Maybe then let's pick up the specific question from Craig, Alex, and then I'll jump back to Ben. Have you looked at the whole life carbon footprint of the solution versus conventional alternatives to deliver the same capacity, or would this be considered in the benefits case?
So we didn't look into carbon footprint. Obviously, the most effective case would be overhead line. And in both projects, we considered applications where overhead lines cannot be used, either urban or if we talk about transmission where overhead lines cannot be used.
Cheers, Alex. Well, I'll come back to you. So yeah, what is the kind of range of potential numbers of breakers needed in GB as per your analysis? Has that been assessed?
Yeah, so it's one of those difficult questions, Manu, because it's a bit of a crystal ball gaze. But based on the phase 1 work, we had at least 16 that would be required, and then you factor in what the success of those 16 would be for then offshoring the technology, and then it would be implemented, we think, across a number of multi-purpose interconnection projects for GB, so that could easily double that number. But then you've got the kind of context more generally of what's going on across Europe. So we have, in addition to the estimates in GB growing from 80 gigawatts of offshore wind by 50 to now about 140, we've got Europe delivering about 350 plus up to about 450 gigawatts in some estimates. You've got Norway recently announcing it's going to deliver 30 gigawatts. So as the technology offshores, you can see North Sea grids being progressively developed using DC circuit breaker technology. And I guess the other kind of feedback loop is we've been informed. I mean, we were really surprised with the detail and the engagement that we saw from the vendors. And one of the points that was feedback was that the economy of scale is there in DC circuit breakers, that they can see as the scale of the breakers increases, as the specifications become more common, then the costs will reduce as a result of that, because you'll be consolidating in these hubs. And so some of the solutions that today look perhaps more attractive compared to DC circuit breakers, that will again skew more towards DC networks in the future. So yeah, there's it's a bit of a crystal ball gaze, as I can say, but certainly significant numbers, and yeah, 52 plus based on the sort of current position that we've got around GB, certainly. So there's certainly a meaty opportunity, I think, for suppliers and others to engage on here. It's not just a few one-offs.
No, thanks, Ben. And that's the lower end of the estimate, and about 50.
Well, yeah, I mean, I guess that's the thing. This could really kind of rocket if, you know, we sort of see DC networks being offshored, and we start seeing hubs in the North Sea connecting all of that 450 gigawatts. But again, a bit of a crystal ball to say how much of that is in GB waters and how much elsewhere. Yeah, there's so many variables here, but yeah, huge opportunity. Yeah.
So I think we can come to our last question, which I think, yeah, from Jan Webb. So these projects seem to be mainly cabling and interconnection improvements. Can you say more about the whole system integration dimensions of the project? Yeah, Ben, do you want to go first, and then I'll come to Alex?
Yeah. I mean, I guess I kind of use the analogy of the road system. So if you went to London, you wouldn't see sort of getting across London being a kind of go through the middle. You go around the M25, and what you're doing with these high capacity DC networks is you're building your equivalent of the motorway infrastructure, which is able to carry large amounts of power to where they need to be that can service the demand. So it's not just about connecting up the offshore wind. It's also about making sure in an environmentally sensitive way that we minimize the amount of assets that we put on the coastlines of the system, but also minimize the overall levels of reinforcement we need on the network to ensure that we're connecting that generation to demand. So just as the original AC system was constructed about where the generators are, so the DC system, which is mostly offshore, will be constructed around where the generation is, but also where it needs to get to, where the demand is. So a lot of these connections will be coming from the north to the south, and you're talking about mainly eastern and western spines. But yeah, exciting stuff for network designers. It's a bit like being in the 1950s and 60s again. Huge amount of growth on the network.
Just when Alex, maybe quick response.
Yeah, I can use the same analogy that the motorway system in the UK, it's a backbone of the economy. So that's both of our projects, either Segil or Skaden, is basically building this motorway system for electricity delivered from renewable generation up to the end consumers for EV heats or urban industries. So that's how we try to deliver benefit to the whole system. If you need electrolyzer, you would still need to get power to use the electrolyzer.
Brilliant. Thank you, Alex. Thanks, Ben. Thank you so much. I think we've come to the end of the session. Really appreciate you taking the time in presenting and taking all the questions. Really appreciate that. So we'll be going to our break now. And then, so I have 10:18 on my clock. Maybe see you guys back in about 9 minutes or so if we can start back. Thank you so much.
Take care. Bye.
Thank you, everyone. We'll come back at 10:30. 10:30, let's say. Alex, if you can make your way over to the other session, that would be great. Thank you.